Hi everyone, my name is Julia and today I will talk about a probabilistic method for search in DAG-shaped search spaces that I've been working on for the past month with my advisors Philipp and Cheng. I guess many of you will be familiar with tree search as a special case of DAG search, like it's for example used in AlphaGo Zero, but also outside of the game domain, tree search algorithms are used wherever we need to plan our actions a few steps ahead in the future. The major application that we are working on is tree search for non-myopic feature selection. In these kinds of problems, we may pick a small number of features from a dataset and then make predictions for classification or regression with our selected set of features. A common challenge in these problems is that we want to find good combinations of multiple features and do not want to consider them in isolation. A showcase for this is pixel selection in MNIST images for classification. Let's say you can pick 10 pixels. You wouldn't want all of them from somewhere in the center of your images, even though there would probably be the best locations if you would always consider one pixel on its own. The downside of this is, of course, the combinatorial explosion of the search space. With just 10 pixels out of the 784 pixels of an MNIST image, the number of combinations is already in the order of 10 to the power of 22. Now, let us have a closer look at what the underlying search space looks like and why it's more a general directed acyclic graph instead of a tree. The figure on the right shows a small part of the search space. At the top of our graph, we have the root node that represents the state and that we have not yet observed any feature. The root has a child for every feature in the dataset. Then in the next level, nodes represent combinations of two features and so on until we get to the level of the leaves, where nodes contain the final number of features, like the 10 pixels of the MNIST images. We assume that the total number of features we may select is fixed and also that we have to select the same features for all instances. Furthermore, we have an oracle available that we can ask for the accuracy for partial classification with a certain feature combination. That's what we use as the reward at the leaf nodes. The objective is then to find the path that leads to a leaf with the highest reward. Since we are only interested in the final combination of features, the order of the feature sequence we got there does not matter to us. We don't care if we first select feature X and then feature Y or the other way around, which is why the two paths join and we end up with a DAG instead of a tree. By going from a tree to a DAG, we collapse nodes that represent identical states. With our probabilistic version of DAG search, we generalize the idea of identical states to similar states. As long as states are not identical, we don't collapse them, but we can still use the information that we collected for one state for other states that are known to be similar to it. Let's say we make a rollout from node xy and end up in a leaf node that also contains featured z. Then the observed reward not only tells us something about node xy, but also about node z, or any other nodes that we know to be similar to the leaf node. In the underlying probabilistic model for the DAG, we have two values for each node, generative scores and optimal values. And the generative scores are the ones that we use to capture similarity between states. The generative scores model the expected reward from a state if the remaining decisions are made randomly. As opposed to the optimal values, we can assume that they are smoothly distributed over the search DAG and then we model them with a joint Gaussian. The covariance is chosen in a way that reflects the similarity between states. For example, in DAG search for feature selection, we define it as the number of shared features in the feature bags represented by two nodes. Of course, it has to be properly scaled. For the rewards at the leaf nodes, we assume a Gaussian likelihood with a small noise scale. This basically fixes the generative scores of observed leaves to their rewards. Whenever we observe a new reward, we can update our Gaussian model for the generative scores by doing a Gaussian regression. Then, as long as a node has a non-zero covariance with a leaf node, An observation there will influence the node score even if the rollout began at a node from a completely different part of the search DAG. In the end, we don't want to know the score of a node under the assumption that decisions are made randomly, but we want to know the value of decisions if we make all subsequent decisions optimally. That's what the optimal value of a node is there for. For a leaf node, the optimal value and generative score are equal since there are no subsequent decisions left, and for inner nodes, the optimal values are defined recursively as the maxima of children nodes. Of course, we cannot have the complete DAG in memory and compute the recursion to its end. We need beliefs for the optimal values of nodes at the current boundary of our DAG that we have explored so far. To arrive at beliefs for the optimal value for a node at the boundary, we use its generative score that models the value under random decisions and then add another term, delta, to it. That indicates how much we can improve the score if we make the remaining decisions optimally, rather than random. The idea to model the optimal values in this way comes from a tree search method developed by Philipp when he did his PhD with Microsoft Research. I won't go into details now how to construct beliefs over the deltas, but the underlying idea is to assume a Brownian random walk for the remaining decisions by always adding a scaled Brownian step C to the parent's generative score. And with these C, we can derive beliefs for the deltas. At the leaf node, the deltas are 0, since the optimal value of a leaf matches its generative score. And for nodes one level above, we need the maximum of the C for the children leaves, and so on. And here we need the maximum of Gaussian random variables. The distribution of the maximum is not a Gaussian anymore, but we approximate it with one using moment matching. Since the definition of the delta is the same for all nodes on the same level of the DAG, it is possible to construct this lookup table for the deltas in less than exponential time. Then, for nodes at the boundary, we can just add the two Gaussian beliefs together, the one we have for the generative score and the one for the delta, to get a belief for the optimal value. For the inner nodes, we again use a moment matching based Gaussian approximation. The beliefs capture our uncertainty over the optimal values that we can use in our policy to guide the search not only to nodes that promise high rewards, but also to those that we don't know much about yet. Now that we're enough technical things, let's move on to some empirical results. We compared our probabilistic DAG search to several other tree search methods on the MNIST problem. The figure on the left shows the accuracy for MNIST images with partial classification based on the pixel combination that is considered best at the respective search step. The bottom three curves belong to tree search algorithms that cannot share information across the search tree and do not generalize. The light blue is a version based on Monte Carlo sampling and rave scores that also allows for some form of information sharing. And probabilistic DAG search, the red one, performed best. And on the right side you can see the final set of 10 pixels that we found with our method. I would like to end my talk with a summary of where I am with my project and where I want to go. We have a version of probabilistic DAG search for non-myopic feature selection that was, at least in our experiments, more sample efficient than approaches based on Monte Carlo sampling, due to its ability to generalize between similar states across the search space. At the moment, it returns the same set of features for all instances, but in practice, this can be quite a restriction, which is why we're currently exploring how to modify the approach to deal with individual feature sequences for different instances. Thank you.